Again, the slides are all available at the Git repository. If you want to follow along in your own desktop, you can clone the GitHub repository and then you get the slides. Okay, so maximum inner product search, what it is? So this is a formal definition. So given a query XU, in this case we denote as a user vector, and we need to determine the index of the item that return the highest inner product value. And as Hardy explained, right, maximum inner product search is not equivalent to nearest neighbor search due to the difference in the nature of the matrix that define the problem. Maximum inner product search is based on inner product score, whereas nearest neighbor search is based on Euclidean distance or L2 distance. So a quick overview of what are possible approaches to solve maximum inner product search approximately. So one approach is that you narrow down the search space by filtering out the candidates to do the exact inner product search computation. And this can be done via either locality sensitive hashing or inverted indexing. The other approach including sampling, which also reduce the number of candidates you need to perform the exact inner product search. And then you have sequential scanning. Basically, you perform the sequential scanning over all the item vectors, but you apply some branch and bound technique to basically have an early stop mechanism to cut down the cost of of scanning over through all the possible items. And then lastly, there is this approach which is quantization-based. So this approach is basically reducing the cost of a particular inner product computation. So that you can imagine that either you narrow down the search space by reducing the number of candidates, so that you need to perform less number of inner product computation, or you reduce the cost of a particular inner product computation. So that's the two possible approaches. So I'm going to move to the first part, which is different approaches to reduce the number of items that you need to investigate. Okay, so the first idea is based on locality sensitive hashing. So that's a summary of from the previous part, in which we have this negative result, which is there cannot exist any classic locality sensitive hashing for maximum inner product search, and you can find the proof of this result in the paper of Srivastava and Lee, which he published in MIPS 2014. So since there doesn't exist classic locality sensitive hashing scheme for maximum inner product search, so you need to have a way to work around to solve this problem. And what Srivastava and Lee proposed in their papers is that you need to perform some transformation to reduce or transform maximum inner product search to nearest neighbor search. So we have the original query vector XU, and it is the item vector YI. So you can define this asymmetric transformation. Asymmetric means that for query vector you have different transformation, and for the data vector or item vectors you apply different transformation. So specifically, right, for user vector or query vector, you just add more zeros towards the end of the vectors, and for the item vectors you add more power of the norm of the item vectors. Which assumption is that all the item vector has a norm lesser than 1. And this can be achieved by just scaling the item vectors with the max norm of all the possible item vectors. So with this transformation, right, you have the following observation, which the inner product of the transform vectors is basically can be defined through the inner product of the original vector xu and yi plus the some power of the item vectors. And based on this observation, you have the next observation in which the inner product of the original vectors can be approximate through the Euclidean distance of the transform vectors. So what is the takeaway from this is that after the transformation, right, maximum inner product search of the original vectors now becomes the nearest neighbor search of the new transform vectors. And effectively, you transform maximum inner product search to nearest neighbor search. Okay, any questions? Yeah, so then maximum inner product search now has become nearest neighbor search, which now you can use locality sensitive hashing that solve for L2 distance to solve maximum inner product search. So this is just to say that the newly defined locality sensitive hashing scheme is efficient to solve maximum inner product search in sublinear time, meaning that it's sublinear to the number of items. So then they derive a generic recipe to construct any asymmetric locality sensitive hashing schemes, which basically you have a particular similarity of interest. In this case, is defined as a function of the query vector and the data vectors. And for our particular problem of recommendation retrieval, then the similarity is inner product. And then you construct a transformation function P and Q for data vector and query vectors. And the requirement is that the similarities defined for the transform vectors should be monotonic with respect to the original similarity of interest. So if you go back to this observation, right, then this is a the new similarity based on the new transformation vectors is actually a monotonic function of the inner products between the original vectors. So then, because these new similarities is a similarity kernel in which there exists a locality sensitive hashing scheme to solve it efficiently. So then you apply the locality sensitive hashing to solve the maximum inner product search. All right. So then, based on this generic recipe, right, the same authors actually propose another transformation scheme that makes use of that try to reduce maximum inner product search to maximum cosine similarity search. Then basically the idea is that they also augment the original user vector and item vectors into higher dimension space, in which maximum inner product search of the original vectors becomes maximum cosine similarity in the augmented vectors, for the augmented vectors. Yeah. So a couple of results that they performed to testify the effectiveness and the efficiency of the asymmetric locality sensitive hashing. So here the metrics that they use for comparison is precision and recall. And you can see that the new the asymmetric locality sensitive hashing scheme, which is based on cosine similarity, is actually performed better than the asymmetric scheme proposed for L2 distance. This figure is to compare based on the recall and the fraction of multiplication. The fraction of multiplication is actually the number of inner product that computation that you need to perform to determine the tokay. So if you see this diagram particularly right with the same level of recall value, then the number of inner product computation that the side asymmetric LSH scheme needs to perform is actually lower as compared to L2 LSH. So this is to say that the asymmetric LSH scheme for cosine similarity is actually more efficient as compared to the LSH scheme for L2 distance. But however, later, right, Nesabu and several actually saw that there is even more simple transformation to reduce maximum inner product search into nearest neighbor search and maximum cosine similarity search, which effectively they only need to augment the user vector and item vectors into one more higher dimensional space by just appending 1, 0 value to the user vectors and make sure that all the item vector now has the same norm. And with this transformation, effectively you convert inner product search into nearest neighbor search and maximum cosine similarity search. So the whole idea of reducing maximum inner product search to nearest neighbor search or cosine similarity search is that you convert the inner product search into the problem that you can solve effectively using existing classic locality sensitive hashing. In this case is nearest neighbor search and maximum cosine similarity. So any questions so far for this approach? Okay, if no, then so this is basically a simple illustration of how you can transform the vectors so that you convert maximum inner product search into nearest neighbor search. So this is the original vectors, and this is the transform vectors. So after the transformation, right, all the item vectors now become a points on the unit sphere. And with this transformation, then maximum cosine similarity becomes nearest neighbor search and maximum cosine similarity search. Yeah, and so a couple of experiments taken from the papers. You can see that the hashing qualities of this simple LSH scheme is actually better as compared to the previous two asymmetric locality sensitive hashing schemes in terms of the hashing qualities. This quantity is defined as a metric to evaluate the quality of the hashing. As compared in the real data set, then both precision and recall of the simple LSH scheme is actually showing better result as compared to the L2 asymmetric LSH and the side random hashing. So that is to say that by actually transforming the user and item vectors into just one more dimension, higher dimension, you can actually achieve a better retrieval result while still maintaining high accuracy of the recommendation result. So later in the hands-on session, we're going to do some experiment with this simple LSH. That basically we only need to transform the user vectors and item vectors into one more higher dimension space. And based on that transformation, we can achieve fast retrieval and also guarantee the accurate recommendation result. However, right, even with the Xbox transformation, there are still some drawbacks that you might encounter. So if you look at this figure, right, so this is this is data vector, and the Q1 is query vectors. So this is the original form of the data vector and the query vectors. So after the Xbox transformation, the two data vector now become 2 points on the circle, whereas the query vector becomes a point of Q2. Sorry, it's still Q1. But the basic idea is that if the norm of the query vectors is too small, then after the transformation, the transformation affects the ranking. So original representation, right? You can see that O2 is very close to the query vector Q1 as compared to O1. But after the transformation, this basically the distance between the new query and the new vectors basically become similar. So what could be the consequence of this? The consequence is that the result of the retrieval that you get based on the new transformation could be arbitrarily bad. And it could happen the same if the norm of the query vector is much bigger than the norm of the data vectors. However, for the recommendation retrieval problem, because the norm of the query actually doesn't affect the ranking of the items, so then we should not worry about this problem. Okay, so because of the drawback of the Xbox transformation, then the authors of this KDD paper this year, they actually propose another transformation in which you scale the query vectors so that they also become a point on the unit sphere. And because of this, right, the approximation, the distance between the new query vector and the new data point vectors actually not too much different as compared to the distance between the original query vector and the original data vectors. So meaning that what the new transformation actually better preserve the ranking of the data points as compared to the original query vectors. Okay, so that summarizes the approach of vector augmentation that convert maximum inner product search into nearest neighbor search and maximum cosize similarity search, and which you can solve effectively using locality sensitive hashing. So now the second idea is that you can actually make use of inverted index to solve recommendation retrieval. So the idea is proposed in by Pahomik and Avradip in AI Stats 2016 in their paper of geometry-aware mappings for high-dimensional sparse vectors. So the basic idea is that you have the compatibility between the data vector is based on inner product, and the idea is that you want to map this data representation into sparse form. And the idea is that if the two vectors are highly compatible, then you convert them into sparse vectors with similar sparsity patterns. Whereas if the inner product between the two vectors is low, then you convert them into sparse form in which they have very different and very conflict sparsity patterns. So let's quickly go through the mechanisms, right? So there is they normalize all the data vectors and the query vectors. So now they become data points on this unit sphere, and then you tessellate or you partition the sphere into different regions, and for each region you equipped with a permutation scheme. So this is the original data space, and then for each area, you just add more zero value to the ends of the vectors, and then you apply the associated permutation scheme. So the result is like this. So you convert the user vectors and the item vectors into sparse vectors. And what is special about these sparse vectors? If the inner product between the user vector and the item vector is high, then the sparse vectors representation of the user and the items will be very similar. They will have similar sparsity pattern. Whereas if the inner products between user vector and item vector is low, then it results in very different sparsity pattern of their sparse vectors. So what is similar sparsity pattern and what is conflict sparsity patterns? So assume that these are two sparse vectors, right? So you can see that these two sparse vectors, they have non-overlapping non-zero indices. So in this case, we define this as conflict sparsity patterns. Whereas in the second case, if the two sparse vectors have a lot of overlapping non-zero indices, then we define them as having similar sparsity patterns. So if you can see that with two vectors that have complex sparsity patterns, then the inner product between the two vectors will be zero. Whereas if the two vectors have similar sparsity patterns, then it would result in a non-zero inner product computation. Yeah, so that's a quick illustration of how you can use inverted index to do recommendation retrieval. So first you build the index, right? You have item sparse vectors. Then based on the item sparse vectors, you build the inverted index. So the inverted index is constructed as following. So first you consider the first coordinate of the sparse vectors, and then you just list down all the items that has non-zero value in the first coordinate. Similarly, you perform the same things for the second coordinate towards the last coordinate. So the inverted index here is to say that at the first position, the item vectors has non-zero values. The second, the item 2, item 7, and item 8 has non-zero value at coordinate 2. So by the time of doing retrieval, right, you have the user sparse vectors. What you need to do is just to look at the posting list, the list of items of the non-zero indices of the user vectors. In this case is the first coordinate and the fourth coordinate. And the item appear in the list will become the candidates for inner product search computation. So effectively, instead of investigating through all the items in the inventory, now you only need to investigate the candidates that's generated by the inverted index. Any questions? Yes?
So you mean you are assuming that any non-zero entry is positive?
Yes. Yeah, so basically the output of magic factorization methods is going to be dense vector, right? And then they normalize the user and item vectors, and then they apply this transformation so that the user and the item vector now become sparse. Yeah, so basically the assumption is that because the rating range is from 1 to 5, right? And then you can always learn the user vector and item vectors so that the values of the vectors are always positive. So even after the transformation, then the sparse vectors that you get will have all positive elements. but the interesting idea is that instead of operating on the low and dense real value vectors, they actually map it into a sparse vectors so that they can make use of inverted index to efficiently do the recommendation retrieval. Yes?
This sounds very similar to like the Bloom filter type of idea.
I'm sorry?
So, like Bloom filter, there's this hashing of individual things to like different places and you look up.
Oh, so this is not based on locality sensitive hashing. It is based on inverted indexing, in which the mechanism for you to filter out the candidates to do exact inner product computation is based on the inverted index. Yeah. All right. Any more questions? Okay. If not, then I will move on to. So just a few experiment results that they do. They do comparison on the preference data set, in which in this case a Movielens data set. So you can see that as compared to the baselines, then they actually can discard more relatively good number of irrelevant items of users. So this is to say that using this scheme, they can actually discard more irrelevant items for one particular user. Okay. So in terms of recovery, how well you retrieve the relevant items, they also show very good results as compared to the baseline. Basically, you can retrieve more 5-star rating items, 4-star rating items as compared to all the baselines. So they can discuss more irrelevant items. In the meantime, they can recover more relevant items, which is good. Okay, so sampling is a third approach to filter out the candidates to do the exact inner product computation. So the idea of sampling is proposed in this paper published in ICDM 2015. So the problem that they solve is actually a more general problem as compared to maximum inner product search. It is basically maximum all pair maximum all pairs search. So instead of only having one query vectors and you need to do the inner product search for one vector, then you basically solve a more general problem in which you determine the top k pairs of inner product that has the highest inner product of the two matrices. So it is a more general problem in the case that if you only have one row in the A vector here, then it becomes maximum inner product search. This is a maximum all pair inner product search in which you finding the top inner product between the multiplication of the two matrices A and B. So the idea, so that's as a motivating example, right? Then some of the application that you can formulate it as maximum all pairs dot product search is that, for example, if you want to increase the number of reviews on the website of a book, a selling book, then basically you base on the user historical feedback. So let's say this particular user has reviewed this particular book K, and because you also have a matrix of book similarities, if book J is similar to book K, then probably you want to recommend the book J to the user I, so that the user I can read and provide more reviews to the book J. So, you can see, right, if you represent this through a matrix A, which consists of all the viewing history of the user over all the books, and it is the book similarity matrix, then the inner product between any two instances of vector of matrix A and matrix B is actually the number of books reviewed by a particular user to a similar book. So the idea, the approach that they use is based on sampling. So this tripartite graph. So at first they solve the problem in which the inputs are binary matrix. Matrix A and matrix B, the entries are all binary value, either 0 or 1. So basically, the inner product between any row of the two matrix is basically the number of okay. So first, I construct the tripartite graph, in which so this is m elements of matrix A, and n is n elements of matrix B, and d is a dimension of the vectors. So there will be an H between node I to node K in this nodes, and in these nodes, if the value of ik is 1, and similarly it will be there will be an H between K and J if the value of bkj is 1. So what this tripartite graph represents is that the inner product between vector ai to bj is actually the number of connected paths between I and j through any nodes in the middle. So what they want to do is that they want to, so in order to determine the highest, the index of the highest maximum inner product pair between A and B, right? Then they need to sample how you can connect between node I to node J through any nodes in the middle. And this can be achieved through a sampling scheme in which you sample, you start from node I, and then you sample a random node here, and if there is a path, then you first you sample the pair ik, and if there is the path, right, then you continue to sample j from k, and then you just maintain a sampling count by and then whenever you can sample a path from I to j through any node in the middle, then you just increase the value of the sample x, I, and j. So the idea is that after sampling, right, you receive a sampling matrix x, and we just recompute the largest entries of this sampling matrix x for the exact dot products computation. So after this sampling mechanism, right, you get a sampling matrix x, and then you only investigate the highest, largest entries of this sampling x for exact product computation. So this sampling mechanism will give you a way so that you don't need to investigate through all the possible inner product computation at the beginning. You just need to sample a limited number of times, and then you derived with a sampling matrix, and this sampling matrix gives you a hint of what could be the index that returns you the maximum product, inner product. So the sampling mechanism is actually providing a better recall result in short time, and as compared to locality sensitive hashing, is actually showing better recall and precision result. Okay. Any question for the sampling mechanism? So if not, then the last approach is sequential scanning. So in sequential scanning, you actually, based on these inequalities, the cosine swatch inequalities. So just imagine, right, instead of scanning through all the item vectors and perform the inner product computation, you're maintaining a current record. In this case, they maintain a priority queue R to store the Tokay result, and T is actually the smallest inner product value in this priority queue. So at any time, right, if you investigate one particular item, you just need to compare the product of the norm of the query vector and the data vector to the current smallest inner product in the result queue. And if the product of the two norm is smaller than the current best, the current smallest inner product in the queue, then you just terminate the search, because it will never be the candidate for Tokay for the Tokay maximum inner product values. So this branch and bound approach is to have you reducing the number of candidates that you need to do exact inner product computation by maintaining a upper bound for inner product search. Then whenever the norm of the query vector and the data vectors is not higher than the current smallest inner product in the queue result, then you can terminate the search at that point of time. So the basic idea is that you don't need to do all the product computation for all the data vectors anymore. Okay, so lastly is so the previous four approach is to reduce the number of candidates that you need to do exact computation. This quantization-based idea is to reduce the cost of a particular inner product computation. So you can still do linear scanning over all the items. However, the cost of inner product computation can be reduced. So how they do it is basically they need to map each vector into k different subspace, and each of these subspace vectors has the same length. Then basically they need to partition the original data space of x, u, and yi into k subspace, and in each k subspace, each user vector and item vector is represented by a sorted vectors enumerated from 1 to k. And the idea is that the inner product between the original vectors can now be approximated by the inner product of all the vectors in the corresponding subspace. So imagine that you can actually reduce the cost of the inner product computation between two 100 dimension vectors into into 10 inner product of 10 dimension vectors. So with that, right, you reduce the cost of a particular inner product computation. So this is the approach of quantization-based, and apparently they give a better results even compared with our locality-sensitive hashing schemes in terms of recall and precision. This is a result for Netflix dataset. So what we can take away from this is a framework for efficient maximum inner product search. So basically, it has two steps. The first step is before any query request, you construct data structures that process the data vectors. You store all the information about the item vectors in these data structures. And by the time you do the retrieval in which you have the query execute, then there are two necessary steps. The first step is query-dependent pre-processing. You pre-process the query vectors that's corresponding to these data structures. And after the query pre-processing, right, you perform the candidate screening in which you filter out the candidates for inner product search. And after you have the candidates, right, you just do the exact computation and the re-ranking on the candidates items. So that is a framework that you can base on to construct an efficient solution for maximum inner product search. So to summarize, right, efficient recommendation retrieval can be solved via solving maximum inner product search approximately, and there are multiple possible approaches. It can either based on locality sensitive hashing or inverted indexing, or it could be based on sampling mechanisms or product quantization to reduce the cost of a particular inner product computation. So yeah, with that, then I would like to end part one, which is in the approach that solving maximum inner product search approximately. So with this approach, right, it can be seen as a flexible way to do recommendation retrieval. You can train your model with any metric factorization based methods like PMF or BPR, and you can apply any of these mechanisms to solve the retrieval problem efficiently. So this will treat the two phases independently. So that gives you the flexibility of which algorithm you use to train the algorithm, the recommend the algorithms, and how you retrieve the recommendation in real time. Yes. So, any questions about the first strategy?